Okay, I think we will start and other people will join us. So back from the coffee break, I'm very happy to present you Vladonețiu, a serverless builder, and we will enjoy today his talk about architecting seismic intelligence, and I hope this one will shake our minds, let's say.
Yeah, so thank you. Thank you for being here. It's a pleasure. We'll talk about architecting seismic intelligence with a high-performance serverless earthquake alert system. So basically what the cloud and cloud services can do for, let's say, a real problem, a real-life scenario. Who am I? I'm Vladonețiu, cloud development, cybersecurity. So these are like the most, let's say, my main areas, projects in data science domain, data extraction, data model, data pipelines. Multiple security research is done for top Romanian banks. And I'm also AWS community builder in serverless from last year. If you want to contact me, I have there my personal email address, also my LinkedIn, so for ideas, opinions, everything like that, you can contact me there. So here are some intro bullet points, like some questions. For example, the first one, why the need for a high performance earthquake notification system? So the project is mostly focused in Romania, so only in our landscape. It all started I will tell you a little story about Romanian alert applications. So right now in Romania we have an application called Raw Alert, which emits like real-time weather notifications, crash notifications, or critical infrastructure failures. But that application has some flaws, like everybody knows. Those notifications are sent like with some minutes or hours after the event was happening. This is why we came up with an idea. Why not integrating also earthquake notifications? Because right now there are not present in that application, and there is no horizon for that, from what we know from our collaborations with the government. So we kind of started to just dig a little bit about what we could use, what institute could we just talk with, at least to have a collaboration, because we need the data. So basically, the second bullet point is where to find good real-time earthquake data, and that was the moment after we came up with the idea to have the project, basically, where to find like some data, real-time earthquake data. So we found out an institute, which is the Romanian Institute for Seismic Movements, based here in near Bucharest. We contacted them and just asked for some data, API data or everything like that. And we found out there is a project on their yard, done some years ago. They have like some real servers, like based in southeast of the country, like in Vâlcea somewhere. They have some real servers there which emit seismic movements, like every little seismic movements is received, and they just capture that in some hardware systems which emit to a browser kind of application on the internet. So that's the kind of a bottleneck from our side. It's just a notification in the browser, so it's not something that's in real time. And after some discussions, we just grabbed their data and tried to just focus on the time. Because the time here is very, very valuable. Like I've said, the servers are in the southwest of the country. So until the wave is received, like in Bucharest or in Cluj or in Timișoara, there are some couple of minutes, like 2, 3, under 5 minutes, under the real waves are received. So we were thinking how to implement something that's like received, so we can receive some messages before the waves are hitting our towns. And yeah, in that moment, we just focused on how to push real-time notifications, but in, let's say, upfront, that's more reliable than real-time, upfront than the waves are hitting the towns. Why choosing the serverless ecosystem is because we are thinking that we don't need servers to be up all the time, so not 24/7 kind of things. Also from a cost perspective, but also from let's say, to bring something new on the table, we were thinking to just include something that's from the cloud. Why not from the serverless niche? Because me, as some other team members, are in this kind of niche. And we are thinking to choose AWS because it was the let's say, the more friendly to us in that particular moment. The kind of the base architecture for our serverless project is like the first version made like 1.5 years ago. I will start describing at least all the areas, but not the gray ones. Those ones will be described afterwards. What you can see here is, let's say, the skeleton, which is like the gray kind of diagrams, which hold like the Kafka producers, how we call them. So these are from the left, the Kafka producers. Kafka is in the middle, is like the distribution kind of messaging system for the notifications, like the delivery of those. And also the Kafka consumers are in the right, which you can see there also some Lambda functions. So both left and the right are just using kind of serverless Lambda functions in AWS. The yellow ones are for just monitoring kind of things, for dead letter queues. For example, when we have like a failure inside a particular box, like in the producers or in the consumers, like critical kind of events are going to that dead letter queue. And kind of networking thing, latency and everything else goes to a retrial mechanism and just tries to retry the message and to consume it again. With the blue ones, we implemented some kind of monitoring tools for all kind of Lambdas, resources, how much time is involved there, and also the costs are being stored in here. And also for the Kafka distribution system, we have the costs monitored, because the Kafka, in the first version, we were choosing Confluent Kafka. We knew in that moment that it could introduce some latencies. We are working in a kind of to just change this part of the system and just bring it into AWS. With these purple ones, we implemented some kind of CI/CDs for the entire infrastructure, also for the provisioning of the infrastructure, but also for the scaling, auto-scaling up and down. I will show you later on in some other slides. Some scannings of the entire project, like the source code, security things, everything that's there. With this green box, you can see here, that's the application. So we were thinking to have like an application where the critical infrastructure people, or also the civil population afterwards, could subscribe. It could be a web application or a mobile application. In this version, we had a web application just in Kubernetes with some Azure functions which will deliver the API endpoints in that application. As databases, we use Dynamo also for storing the subscribers, the list of users from which will be notified by the entire structure, and also to have like a Dynamo for storing all the data for those subscribers. So this is in let's say bold lines the base architecture in the base version of the project. Like I've said, this is the skeleton of the first version of the notification system. So we have in the left Lambda functions, which will listen on the API endpoints and on the data provided by the government institution. When there is a seismic movement happening, we will just trigger some specific Lambda functions, which will use, we are thinking to use all the capacity of those functions, using like some multi-threading, sending notifications, so aligning the notifications in particular Kafka topics. So every thread is somehow linked to a particular topic. This starts some kind of parallelization from the left and just through the right, when you can see these arrows. So every partition in every topic will trigger a certain Kafka consumer in here. So certain execution of the code, which will just subscribe to a specific user and just notify that user. We were aiming to just have some kind of magnitude check, but this magnitude could be also done by that institute people. Like I've said, in the Kafka topics, there are multiple partitions, topics that we could use. We are aligning number of the topics with some kind of resource in here, so to not have more topics than we have like Lambda functions in the left or for the consumers, to have like a certain scalability in both sides, to not bottleneck the entire pipeline. In here we have the dead letter queues, and also the monitoring and everything else like I've shown you before. The final subscribing method we were using is through SMS, email like ACS from AWS, or Telegram as a backup kind of system, but we are aiming just for these two ones for the moment. The architecture for the Kafka integration, serverless context. So like I've said, in the left we have the APIs, the data from the institution. We have the producers, which are linked with some certain kind of multi-threading in here. We are using like a topic roulette, like on top of what Kafka provides us, like for not overriding the same kind of notifications in the same partitions, like another layer on top. We are aiming to just put every notification on a certain partition, and after that, every partition will trigger a certain code execution for the consumers. So just in a parallel way, every partition will have its own Lambda execution, so its own notification for a certain client. This could also lead, so that was a problem in our side, because a partition or a certain invocation in the Lambda will just notify a certain a person twice or more times than that it should. But we came up with a solution with a kind of a lock, I will describe it later on, which kind of locks a certain execution on a certain user using a custom method. Some key elements, like I presented in the last slides, the multi-threading in the Kafka producer, which is also present in the consumer, using some kind of a thread lock to not write in the same topics from separate threads, and using some partition number to not write data in partitions. This is basically to not, at least to use all the capacity and every kind of logic for achieving that parallelization of notifications. Using the Lambda retry and SQS dead letter for critical errors or just kind of latency networking problems. For the consumer, we have the custom timestamp log. This was this resolved that problem which I was telling you about. So notifying the same person twice or more times. We used that timestamp to just know what user was already notified and to just go to the other one and so on. The optimistic locking is using like a version. So every time a user from the database is under code execution, let's say, so it should receive a notification. That version increases, so we know at the other invocation of the Lambda that we should not notify again that user. Using the Lambda retry and SQS dead letter for errors, and using cold start, warm start, we are thinking to just introduce a kind of a warm start, at least for the consumers, because that's an area that we are using the most. But let's say in these days, we are also aiming to use it for the producers. So to just have some kind of warm instances in the system. I will describe you a bit the first version of the Dynamo locking. So basically how a user is notified from that invocation, which comes from a certain partition from the Kafka cluster. So like I've said, every partition is linked to a certain code execution, so triggers a Lambda code execution, which will act like on a certain user from in here. So here we would have a hospital or something like that with a telephone number or application ID or anything like that. And we don't want that another partition, which is kind of executed at the same time, to act on the same hospital, on the same critical infrastructure. So to just go to the other one. This is a kind of, like we view it like a domino kind of game. And we are reviewing every list of subscribers from the front. And we are just notifying every person just one by one. So it's a kind of a loop in here. This was the first version. Worked pretty well. But again, the entire project was tested at below 5,000 or something like that. The next version of the locking, we are thinking to segment a bit the list of subscribers. So to have like, for example, from 1 to 100, from 100 to 200, certain invocations. So you can see here like a trigger from a topic acts like on a specific segment. So from now on, you can view the Dynamo like row from a lateral view. And every invocation acts on a certain group or on a segment or a certain segment from that group. This was the second version, worked pretty well than the previous one. But again, we didn't use all the capacity of this logic with the trigger coming from the partitions from the Kafka parallelization. So the next one, and what we currently have right now, is like to use maximum triggers, so to allow us on a certain segment more invocations. So for example, for that group, for that segment 1 to 100, to have multiple invocations, and those will act like in the lowest multi-threading option on random users, but not allowing, like I've said, sending multiple notifications to a single subscriber. So using that locking, that versioning for everything, but just allowing more workers on a certain segment. This increased the time by a lot in what we have, but we are trying to just research furthermore and just to see if we could use like a cache kind of system, and if the list of users didn't change, to just have them cached or something like that. The next ones is how to auto scale in the entire project. So yeah, just imagine that all the services are created. So these are created manually. It's not provisioned by anything. In here, you can see that there is a custom code. These are some shell scripts or some API calls, which are just increasing the producers, the Lambda functions, the threads, number of topics in Kafka, provision concurrency, so for the warm start of the consumers, in certain ranges of subscribers. So from time to time, we are just retrieving all the list with of users, of subscribers, and just, let's say, scaling up or down in an automatic way the system. This is also done in the Lambda function, triggered by an event bridge kind of cron job. And this was the first version when we kind of scale the system linked to the number of subscribers. So we cannot know when there is an earthquake just increasing and prepare the entire system because it's kind of tough, but we can use this auto scale for the number of subscribers in a particular moment. The next, this is the kind of the code used in here. So a lot of just logic for increasing the topics or what we need in a particular moment. If the range is in what we need, we just don't increase anything, or we don't scale or anything like that. The custom auto scaling using Terraform and some kind of CI/CD in here is by using, instead of those shell scripts, we were thinking to just provision the entire system using Terraform in this moment. So every kind of service in here, not the Kafka cluster, is created through Terraform. And Terraform is used to just scale the entire system up or down in the same manner, but by just using those kind of ranges for users, which are kept in a custom list inside Git, and we are just kicking that off through Terraform. This is the current kind of state, at least in the auto scaling, because it also gives us the provisioning option, so we don't need to just create things manually. Everything is under infrastructure code. Yeah, like I've said, we are keeping like a list inside the locals in Terraform, and that list is sent to Git, and the GitHub Actions have like a pipeline which just creates the infrastructure, like with more lambdas or with more triggers in the end. Yeah, so this is the current state of the project. We're aiming to have some collaborations with the government or something like that, but it's kind of a tricky collaboration from our end, but we are trying to just to throw something on the table, at least to not create from scratch the Romanian alert, just have an alternative or give some kind of good researches for them. This is kind of all. Yeah, if you have questions, and thanks for everything.
I have two questions, question and a curiosity. You say that the entry point is not necessarily a trigger. You query the APIs that are offered by the government regularly.
Yeah.
What's the frequency? I mean, the aspect needs to be that it has to be processed as soon as possible and send the notification to the end user. Otherwise, it's
exactly. So in this moment is something. So we are not retrieving like it every millisecond, because we could just mess up their servers. We have like an alignment between us. And if they will just, I don't know, create something on their end that will kick the lambdas in our side, or we just retrieve every time. This is a good question.
So every second or something like that?
Every millisecond could be.
But
yeah.
And then comes the second question, where the curiosity. What's the amount of lambdas that you plan to invocate? Because I did the calculations, some calculation before. If you query that each second, you reach 2.5 million per month. Only the lambda that interrogates the APIs. If you say every millisecond, well,
it's a lot.
It's a lot, and perhaps the system that exposed those APIs will crash.
Yeah, this is why the first option, just having on their side some kind of a trigger when that little seismic movement is happening, just trigger something in this.
Yeah, that would be the
kind of
ideal
thing.
case.
Exactly. Because, like I've said, we choose serverless because it's kind of not available all the time. That particular producer, if it's the second case, should be alive every time just to query that data.
And the overall, as a estimation of Lambda invocations, what's your estimation?
In the producers?
Yeah,
or
the
consumers?
whole product.
Like I've said, we only tested like under 5,000 subscribers. So it's not like a lot.
Okay, thank you.
Thank you.
Are there other questions?